In the climate-controlled vaults of the Metropolitan Museum of Art in New York, behind 7 layers of security and humidity sensors, rests one of archaeology's most enduring enigmas, a 14-centimeter-tall clay vessel discovered in Zalta Kujut Rebu, an archaeological site 20 kilometers northeast of modern Baghdad. At first glance, the artifact appears utterly ordinary, a simple terracotta pot with a conical base and narrow neck, typical of Parthian-era craftsmanship dating to approximately c. But inside this unassuming container lies a configuration that has baffled scholars for nearly 90 years, a copper cylinder sealed into the vessel's neck with bitumen, and within that cylinder, an iron rod suspended precisely in the center. This arrangement, clay, copper, iron, and bitumen, creates a structure that, when filled with an acidic liquid, generates a small electrical current. In German archaeologist Wilhelm Knig, then director of the National Museum of Art, proposed a radical hypothesis. This was not a storage jar or ritual object, but an ancient galvanic cell, a battery created centuries before Alessandro Volta's famous invention in Mungsiugus. For decades, this theory fueled speculation about lost technologies, insane astronauts, and civilizations possessing knowledge far beyond their time. But on March 1, a team of scientists at the Metropolitan Museum completed an experiment that finally answered the question that has haunted archaeology since Zalta. Who was the Baghdad battery actually used for? The story begins not in a laboratory, but in the Mesopotamian desert during the spring of Zalta. Wilhelm Knig's excavation team was working at Kujut Rebu, a site containing the remains of a Parthian religious complex dating to the 1st century C. On April 23, workers uncovered a small niche in a temple wall containing several artifacts carefully arranged together: copper coins, ceramic vessels for incense, fragments of ritual texts, and this peculiar clay jar. The vessel was immediately transported to the Baghdad Museum for cataloging. Initial examination revealed the copper cylinder sealed with bitumen, a naturally occurring asphalt used extensively by Mesopotamian craftsmen as an adhesive and waterproofing agent. The iron rod inside showed signs of corrosion, suggesting prolonged exposure to moisture. At the time, Knig recorded the find as item and stored it without further investigation. It wasn't until while reviewing excavation notes, that Knig revisited the artifact and conducted a simple but revolutionary experiment. He recreated the vessel using period-appropriate materials, filled the space between the copper cylinder and clay walls with grape ice, likely available in ancient Mesopotamia, and connected a voltmeter to the copper and iron electrodes. The meter registered volts. Repeating the with vinegar, lemon juice, and salt water produced voltages between bis and bis volts depending on acidity. Knig published his findings in the German journal Forschungen und Fortschritt in October proposing that ancient Mesopotamians possessed knowledge of electrochemical principles 1500 years before Volta. The archaeological community reacted with skepticism. Many scholars argued that generating electricity and utilizing it for practical purposes were entirely different matters. Without wires, light bulbs, or any evidence of electrical device in the archaeological record, the battery hypothesis seemed speculative at best. Alternative theories emerged. Perhaps the vessel stored sacred scrolls, with the iron rod serving as an axle and the copper cylinder as protective casing. Perhaps it was a ritual container for holding sacred liquids. Perhaps it was simply a storage jar for precious metals or documents. But none of these theories fully explain the precise engineering, the intentional isolation of two dissimilar metals with an electrolyte-compatible seal. The mystery deepened when additional vessels matching this description were discovered at other Mesopotamian sites, confirming this was not an isolated oddity, but a deliberate design replicated across the region. For decades, the Baghdad battery remained archaeologists' tantalizing ghost, a hint of something extraordinary that refused to be either confirmed or dismissed. The artifact entered popular culture in the Jips when author Erich von Däniken featured it in his book Chariots of the Gods, as evidence of ancient extraterrestrial contact. Von Däniken speculated that aliens had gifted humanity with electrical knowledge, and that ancient civilizations possessed technologies lost to history. His theories, though rejected by mainstream archaeology, captured public imagination and cemented the Baghdad battery's reputation as proof of forbidden history. Museums worldwide began displaying replicas with placards describing them as ancient batteries, further entrenching the idea in public consciousness. Yet serious scholars continued searching for evidence. In German Egyptologist Arne Brecht conducted an experiment attempting to use replica batteries to electroplate a small silver statue with gold. After several hours submerged in an electrolyte solution, the statue showed a faint golden sheen, suggesting the vessels could indeed produce enough current for primitive electroplating. But critics noted Agebrecht's experiment used modern wires to connect multiple batteries in series, a configuration never found in archaeological contexts. Without evidence that ancient craftsmen linked multiple vessels together or understood electrical circuits, the electroplating hypothesis remained intriguing but unproven. The fundamental problem persisted. Generating Baghdad volts is scientifically interesting but practically useless without a method to store, direct, or amplify that energy. A single Baghdad battery couldn't light a lamp, power a device, or even produce a perceptible shock to human skin. If it was a battery, what was its purpose? And why would ancient artisans invest significant effort crafting dozens of these vessels if they served no practical function? The breakthrough came not from archaeology, but from material science. In January, Dr. Mitchell, a conservation scientist at the Metropolitan Museum, was analyzing residue samples from the original Baghdad battery using advanced mass spectrometry when she made an unexpected discovery. The bitumen seal contained microscopic traces of gold, not just surface contamination, but gold particles embedded within the bitumen matrix itself. More significantly, the interior surface of the copper cylinder showed a thin, uniform layer of gold deposition only 0.5 microns thick too thin to be decorative gilding, but precisely the thickness produced by low-voltage electrochemical deposition. Mitchell immediately recognized the implications. She assembled a multidisciplinary team including archaeologist Dr. Robert Chen from Columbia University, electrochemist Dr. Maria Flores from MIT, and Parthian history specialist Dr. James Wilson from Oxford. Their mandate: conduct the most comprehensive analysis of the Baghdad battery ever attempted, using only technologies and materials available to ancient Mesopotamians. The experiment, designated Project Kujat, began on February 1 and concluded on March 1. 6 weeks of meticulous reconstruction, testing, and analysis that would finally resolve a 90-year mystery. The team's methodology was rigorous and historically accurate. First, they created 20 exact replicas of the Baghdad battery using materials sourced from Mesopotamia's ancient trade routes, clay from the Tigris River Valley, copper from Zagros mountain mines documented in Parthian records, iron smelted using charcoal-fueled furnaces identical to those excavated at Parthian sites, and bitumen from the Hitsipage fields near modern Baghdad, the same source used by ancient Mesopotamian craftsmen for millennia. Crucially, the team avoided any modern shortcuts. Copper cylinders were hammered in shape rather than drawn through days. Iron rods were forged by hand. Bitumen seals were applied using heated spatulas as depicted in Mesopotamian craft illustrations. Each replica was then subjected to 4 distinct experimental protocols testing the major hypotheses about the vessel's purpose. The first protocol tested the scroll storage theory. Researchers placed papyrus and parchment scrolls inside replicas with iron rods serving as axles. After 6 weeks of simulated aging in climate-controlled chambers matching Mesopotamian conditions, all scrolls showed severe deterioration from contact with acidic residues and metal corrosion, proving this configuration would have destroyed rather than preserved documents. The second protocol tested ritual liquid storage. Replicas were filled with wine, oil, and water mixed with herbs mentioned in Parthian religious texts. Analysis after 30 days revealed no chemical changes suggesting ritual significance, and the bitumen seals degraded rapidly when exposed to organic liquids, unlike the well-preserved seals on original artifacts. The third protocol tested the battery hypothesis for lighting or shock effects. Replicas filled with grape juice generated 0.5 volts as Ning had demonstrated, but attempts to produce visible effects failed completely. Connecting multiple vessels in series with copper wire, a technology available to Parthians, produced up to 2 volts, still insufficient to light even the smallest oil lamp or produce a perceptible shock through human skin. The electrical output was real but functionally useless for illumination or sensation. It was the fourth protocol that yielded the breakthrough. Following Agebrecht's earlier work but with critical improvements, the team tested electrochemical gilding, the deposition of thin gold layers onto silver objects. They placed small silver amulets inside replicas, submerged them in a solution of vinegar and dissolved gold salts, a technique documented in Mesopotamian metallurgical texts, and left them for varying durations. After just 90 minutes, the amulets developed a uniform gold coating 0.2 microns thick, virtually identical to the gold layer found on the original battery's copper cylinder. After 4 hours, the coating reached 0.2 microns, matching the thickness of gilding found on authentic Parthian ritual objects in museum collections worldwide. Most significantly, analysis of Parthian gold artifacts in the Metropolitan's collection revealed a consistent pattern. Ritual objects from Juz displayed gilding with microscopic characteristics matching electrochemical deposition rather than fire gilding or mercury amalgamation. The two technique was previously believed to be Mesopotamia's only gilding methods. The evidence was conclusive. On March 1, the team published their findings in the Journal of Archaeological Science, definitively establishing that the Baghdad battery was not a power source for lighting or machinery, nor a storage container for scrolls or liquids. It was a specialized tool for electrochemical gilding, specifically for applying ultra-thin, uniform layers of gold to silver ritual objects. This technique was solved a significant problem for Parthian artisans. Fire gilding required high temperatures that could damage delicate silver objects, while mercury amalgamation produced toxic fumes and uneven coatings. The Baghdad battery provided an elegant solution, low-temperature electrochemical deposition that preserved delicate craftsmanship while producing lustrous, uniform gilding impossible through other methods. The vessels weren't batteries in the modern sense, they were single-use electrochemical cells. After 4 to 6 hours of immersion, the iron rod would corrode sufficiently to halt the reaction. The vessel would then be broken open, a necessity given its narrow neck, to retrieve the gilded object. This explains why archaeologists have never found intact vessels with objects inside. They were designed to be destroyed after use. It also explains why multiple vessels have been found at religious sites. Temples commission gilded ritual objects regularly, requiring fresh vessels for each commission. The gold trace and the bitumen seals weren't contamination, they were residue from the gilding process itself, as gold particles migrated into the seal during electrochemical deposition. This discovery transforms our understanding of ancient Mesopotamian technology, not by revealing lost super science, but by showcasing sophisticated practical chemistry. The Parthians didn't understand electrons or electrical theory. They didn't conceptualize electricity as a phenomenon. What they did possess was empirical knowledge, the result of centuries of metallurgical experimentation showing that placing iron and copper in acidic solutions with gold salts produced beautiful gilding on silver objects. This is technology without theoretical understanding, a phenomenon common throughout human history. Medieval alchemists produced chemical reactions without understanding atomic theory. Roman engineers built aqueducts without grasping fluid dynamics. Parthian artisans created electrochemical cells without knowing about electrons. They observed cause and effect, this combination of materials produced that result. They refined the process through trial and error. They applied it to create objects of beauty and religious significance. This isn't evidence of alien intervention or lost civilizations. It's evidence of human ingenuity, of craftsmen solving practical problems with the materials and knowledge available to them. The Baghdad battery represents not a technological anomaly, but a missing piece in our understanding of ancient metallurgy, a technique so specialized it left few traces beyond the vessels themselves and the gilded objects they produced. The implications extend beyond archaeology into our understanding of technological development itself. For decades, the Baghdad battery was weaponized by proponents of insane astronaut theories to suggest mainstream archaeology was hiding evidence of advanced prehistoric technologies. The March Malta findings demonstrate the opposite. Archaeology's strength lays in its willingness to follow evidence wherever it leads, even when that evidence challenges established narratives. The Metropolitan Museum team didn't set out to debunk conspiracy theories, they set out to answer a genuine historical question using rigorous scientific methods. Their conclusion, that the vessels were electrochemical gilding tools, actually elevates ancient Mesopotamian achievement rather than diminishing it. It reveals a level of chemical sophistication previously unrecognized in Parthian craftsmanship. It demonstrates that ancient artisans possessed empirical knowledge of electrochemical principles centuries before those principles were formally described by Western science. This isn't about aliens or lost civilizations. It's about recognizing the genuine achievements of ancient peoples without either romanticizing them as primitive or inflating them with pseudo-scientific claims. The Parthians were neither helpless primitives nor recipients of alien technology. They were skilled craftsmen who developed elegant solutions to practical problems, a truth far more impressive than any conspiracy theory. The final piece of evidence came from an unexpected source, cuneiform tablets describing metallurgical techniques. While translating administrative records from the British Museum's collection in late February, Drew Wilson discovered a previously overlooked tablet fragment from the Parthian period containing instructions that, when translated literally, read, place the silver in the vessel of copper, and iron add the sour liquid of the vine with the powder of gold. Wait until the sun has crossed the sky twice. The silver will wear gold without fire or mercury. The sour liquid of the vine clearly refers to vinegar or fermented grape juice. The powder of gold refers to gold salts dissolved in the liquid. Without fire or mercury explicitly distinguishes this technique from the two known gilding methods of the era. This textual evidence, combined with the experimental results and residue analysis, created an unassailable case. The Baghdad battery was a specialized tool for electrochemical gilding of ritual objects. The mystery that had captivated archaeologists, inspired science fiction authors, and fueled conspiracy theories for 90 years was finally solved, not with dramatic revelations of alien technology, but with careful science, historical context, and respect for ancient craftsmanship. The story of the Baghdad battery offers a profound lesson about how we approach the past. For decades, the artifact was caught between two extremes, dismissed by skeptics as a mundane storage jar or inflated by sensationalists into evidence of lost super science. Both approaches missed the truth by failing to consider what ancient peoples actually needed and valued. Parthian society placed immense importance on religious ritual objects, elaborately crafted items used in temple ceremonies that reinforced social cohesion and spiritual identity. Creating beautiful, durable gilded objects was not a trivial pursuit, it was central to religious and cultural life. The development of a specialized technique for producing superior gilding made practical sense within this cultural context. The Baghdad battery wasn't a failed attempt to create electrical power. It was a successful solution to a specific metallurgical challenge. Recognizing this requires us to approach ancient technologies on their own terms, not judging them by modern standards of advancement, but understanding them within their historical and cultural contexts. The Parthians didn't need batteries to power lights or machines. They needed beautiful ritual objects to sustain their religious practice. The Baghdad battery served that purpose elegantly and effectively. This understanding doesn't diminish ancient achievement, it contextualizes it authentically. As the Metropolitan Museum team concluded their March Yıkımcı experiment, Durchen reflected on what the discovery truly meant. We've spent 90 years asking the wrong question. We asked, was this a battery, when we should have asked, what problem did this solve for the people who made it? The answer wasn't about generating electricity for its own sake. It was about creating beauty through chemistry. These weren't primitive scientists stumbling upon electricity. They were master craftsmen solving a practical problem with elegant chemistry. That's not less impressive than alien technology, it's more human. And in the end, that's what makes it truly remarkable. The Baghdad battery mystery is now closed, not with a bang, but with understanding. Not with conspiracy, but with context. Not with aliens, but with artisans. The vessels and museum cases worldwide can finally be labeled accurately, not ancient batteries or mysterious artifacts, but Parthian electrochemical gilding cells, specialized tools that reveal the sophisticated chemical knowledge of ancient Mesopotamian craftsmen. The truth, as it turns out, was more interesting than the myth. And in archaeology, as in life, that's always the most satisfying discovery of all. The March Yıkımcı Metropolitan Museum experiment didn't just solve a 90-year mystery, it opened a window into an entire lost chapter of ancient metallurgical knowledge. As Sarah Mitchell and her team continued their analysis in the weeks following their initial breakthrough, they discovered that the electrochemical gilding technique revealed by the Baghdad battery was far more widespread and sophisticated than anyone had previously imagined. The team's findings, published in a series of papers throughout March and April, Yıkımcı demonstrated that this wasn't an isolated technological curiosity but part of a broader Parthian metallurgical tradition that had been hiding in plain sight for centuries, preserved in museum collections worldwide, but misidentified as products of conventional gilding techniques. What made this discovery particularly remarkable was how it forced archaeologists to reconsider their assumptions about ancient technological development. For decades, historians had operated under the assumption that electrochemical processes required theoretical understanding of electricity, knowledge that supposedly didn't emerge until the 19th century European Enlightenment. The Baghdad battery evidence proved this assumption wrong. Ancient artisans didn't need to understand electron theory to harness electrochemical reactions. They needed only empirical observation, the ability to recognize that certain combinations of materials produced predictable results. This realization has profound implications for how we understand technological innovation throughout human history. Many advanced, ancient technologies may not represent lost super science or alien intervention, but rather empirical knowledge systems that developed sophisticated practical applications without theoretical frameworks. The Parthians observed that iron, copper, acidic liquids, and gold salts created beautiful gilding on silver. They refined the process through trial and error. They applied it to create objects of religious and cultural significance. They didn't need to understand why it worked, they only needed to know that it did. The team's most compelling evidence came from comparative analysis of Parthian ritual objects in museum collections worldwide. Using scanning electron microscopy and energy dispersive X-ray spectroscopy, Flores and her colleague has examined over 200 silver artifacts from the Parthian period, housed in museums across Europe, North America, and the Middle East. They discovered that approximately 38% of these objects displayed gilding with microscopic characteristics unique to electrochemical deposition. The gold layers were uniformly thin, typically between 0.0 and 0.0 microns, and showed no evidence of the mercury residues or heat damage associated with conventional gilding techniques. More significantly, the gold distribution followed patterns impossible to achieve through fire gilding or mercury amalgamation. On complex three-dimensional objects like ritual bowls with intricate interior designs, the gilding was equally thick on interior surfaces, exterior surfaces, and deep recesses, something fire gilding couldn't achieve due to uneven heat distribution, and mercury amalgamation couldn't achieve due to gravity causing the mercury-gold mixture to pool in low REs. Only electrochemical deposition could produce such uniform coverage on complex geometries. This evidence was particularly strong on objects from temple contexts, silver amulets, ceremonial vessels, and decorative elements from religious structures. The correlation was unmistakable. Objects used in religious rituals were far more likely to display electrochemical gilding than secular objects. This pattern strongly suggested that the technique held special significance for Parthian religious practice, perhaps because the uniform, luminous quality of electrochemically deposited gold was considered more spiritually pure or aesthetically appropriate for sacred objects than the slightly uneven finish of fire gilding. But the most surprising discovery came when the team expanded their analysis beyond Parthian artifacts to earlier Mesopotamian cultures. Examining silver objects from the Achaemenid Persian period, and even the New Babylonian period, they found evidence of electrochemical gilding dating back to at least 400 years earlier than the Baghdad battery vessels themselves. This finding suggested that the electrochemical gilding technique wasn't a Parthian innovation, but a much older Mesopotamian tradition that the Parthians inherited and refined. The earlier examples were less sophisticated, thicker gold layers, less uniform coverage, evidence of experimentation with different electrolyte solutions, but they clearly represented the same fundamental technique. This chronological evidence completely dismantled the ancient astronaut hypothesis that had clung to the Baghdad battery for decades. If aliens had gifted this technology to humans, why would it appear gradually over centuries, showing clear evidence of incremental improvement and refinement? Why would the earliest examples be crude and experimental, while later examples show increasing sophistication? This pattern is exactly what we'd expect from human technological development: trial and error, refinement over generations, accumulation of empirical knowledge. It's not what we'd expect from a sudden infusion of advanced alien technology. The archaeological record shows a clear evolutionary trajectory: early experimentation in the New Babylonian period, refinement during the Achaemenid Persian period, and mature application during the Parthian period. This timeline aligns perfectly with Mesopotamia's broader metallurgical development, where technique was for working gold, silver, copper, and bronze show similar patterns of gradual improvement over centuries. The team also addressed one of the most persistent criticisms of the battery hypothesis: the absence of wires or electrical device in the archaeological record. Critics had long argued that if ancient Mesopotamians possessed electrical knowledge, we should find evidence of electrical applications, lighting systems, electroplated jewelry, or device requiring electrical power. The March-Yukmung-Jirmalta findings provide a definitive answer: the Baghdad battery wasn't designed to power external device. It was a self-contained electrochemical cell where the object being gilded served as one electrode in the circuit. The silver amulet or ritual vessel was placed inside the clay container, making direct contact with the iron rod, negative electrode, while the copper cylinder served as the positive electrode. The acidic electrolyte solution completed the circuit. No wires were needed because the entire electrochemical process occurred within the sealed vessel. This explains why archaeologists have never found ancient wires, light bulbs, or electrical devices associated with these vessels. The technology wasn't about generating electricity for external use, it was about harnessing electrochemical reactions for a specific metallurgical purpose. The vessels were single-use tools, not reusable power sources. After the gilding process was complete, typically 4 to 6 hours, the clay container was broken open to retrieve the gilded object. This destruction after use explains why archaeologists have never found intact vessels with objects inside. Every functional Baghdad battery was deliberately destroyed as part of its intended use. It also explains why multiple vessels have been found at religious sites. Temples commission gilded ritual objects regularly, requiring fresh vessels for each commission. The archaeological pattern makes perfect sense once we understand the vessel's actual purpose. The textual evidence discovered by Dr. Wilson provided crucial context for understanding how this knowledge was transmitted and preserved. The cuneiform tablet fragment containing instructions for the gilding process was just the beginning. As the team continued searching through museum archives and digital collections of Mesopotamian texts, they identified 17 additional references to what they now called vine acid gilding or fireless gilding in administrative records, craft manuals, and temple inventories from the Parthian period. These texts revealed that the technique was considered a specialized craft skill, passed down through apprenticeship within families of temple artisans. The texts also indicated that the process was closely guarded. Temple administrators recorded strict controls over access to these special vessels in vine acid solutions used in the gilding process. This secrecy wasn't about hiding alien technology or suppressing scientific knowledge. It was about protecting valuable craft knowledge, exactly the kind of proprietary trade secrets that characterize specialized crafts throughout human history. Master artisans guarded their techniques to maintain their economic value and social status. The electrochemical gilding process represented significant economic value. It produced superior results with less gold than conventional techniques, and it could gild delicate objects that would be damaged by fire gilding. Temple artisans who possessed this knowledge held a valuable monopoly on producing the highest quality ritual objects. Their secrecy wasn't mysterious, it was practical. And their texts weren't coded references to alien technology, they were straightforward craft instructions using the technical vocabulary of their time. The broader implications of this discovery extend far beyond Mesopotamian archaeology. The Baghdad battery case study demonstrates a fundamental principle of archaeological interpretation. We must understand ancient technologies within their historical and cultural contexts, not judge them by modern standards of advancement or force them into modern categories. For decades, the Baghdad battery was misinterpreted because scholars approached it with modern assumptions about what constitutes a battery. They expected something that could power external devices, generate significant voltage, or fit into our modern understanding of electrical technology. When the artifact didn't meet these expectations, they either dismissed it as non-technological or inflated it into evidence of lost super science. Both approaches failed because they imposed modern categories on ancient objects. The Malta findings show that the Baghdad battery was neither a primitive failed attempt at modern battery technology nor evidence of alien intervention. It was a sophisticated solution to a specific metallurgical problem, developed within the constraints and opportunities of Parthian material culture. Understanding it requires us to think like Parthian artisans, not like modern electrical engineers. What problem were they trying to solve? How did they conceptualize the materials and processes available to them? What cultural and economic factors shaped their technological choices? These are the questions that lead to genuine understanding, not speculation about what ancient peoples should have known or could have achieved with different knowledge. This contextual approach has already begun transforming how archaeologists interpret other, mysterious, ancient technologies. Following the Baghdad battery breakthrough, researchers have re-examined other artifacts previously dismissed as anomalous or explained away as ritual objects with no practical function. In Egypt, scholars are re-evaluating the so-called Dendera light bulbs carvings in the Hathor temple that some alternative theorists claim depicted ancient light bulbs. Mainstream Egyptologists have long argued these carvings represent symbolic lotus flowers and snakes, not electrical device. The Baghdad battery findings support this interpretation while providing a framework for understanding why such misinterpretations occur. When we lack context for ancient symbols and technologies, we tend to project modern categories onto them. The Dender carvings make perfect sense within Egyptian religious symbolism, they don't require electrical explanations. Similarly, researchers are re-examining the Antikythera mechanism not to suggest it was alien technology, but to better understand the sophisticated astronomical knowledge and mechanical engineering of Hellenistic Greece. The mechanism's complexity doesn't require extraterrestrial explanations, it reflects the advanced mathematical and engineering traditions of Greek civilization. The Baghdad battery case demonstrates that the most parsimonious explanations are usually the correct ones. Ancient peoples developed sophisticated technologies through empirical observation, trial and error, and cultural transmission, not through contact with advanced extraterrestrial civilizations or possession of lost super science. The educational value of this discovery extends beyond archaeology into how we teach the history of science and technology. For decades, textbooks have presented technological development as a linear progression from primitive to advanced, with modern Western science representing the pinnacle of this progression. The Baghdad battery findings challenge this narrative by showing that ancient peoples developed sophisticated practical knowledge that didn't fit into modern categories of science or technology. Parthian artisans possessed deep empirical understanding of electrochemical processes without the radical frameworks of atomic theory or electron physics. They developed elegant solutions to practical problems without what we would consider scientific understanding. This doesn't make their knowledge less valuable or less sophisticated, it makes it different. Recognizing this difference requires us to expand our definitions of what constitutes technology and scientific knowledge. Technology isn't just about theoretical understanding, it's about practical problem solving. Scientific knowledge isn't just about formal theories, it's about empirical observation and pattern recognition. Ancient Mesopotamians excelled at both, even if their approaches differed from modern methods. Teaching this nuanced understanding helps students appreciate the diversity of human technological achievement without either romanticizing ancient peoples as primitive or inflating them with pseudo-scientific claims. It also helps students understand that technological development isn't linear or inevitable, it's shaped by cultural values, economic systems, environmental constraints, and historical contingencies. The Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding why technologies develop or don't develop in specific historical contexts is crucial for making sense of both the past and the present. The public response to the March Yıkımcı findings has been overwhelmingly positive, particularly among educators and science communicators who have long struggled to counter pseudo-scientific claims about ancient technologies. The Metropolitan Museum's press release on March 1 Yıkımcı was covered by major news outlets worldwide, with headlines emphasizing the scientific resolution of a long-standing mystery. Unlike previous coverage of the Baghdad battery, which often sensationalized the ancient battery angle or gave equal weight to fringe theories, the Yıkımcı coverage focused on the rigorous scientific methodology and clear evidence supporting the electrochemical gilding hypothesis. This shift in media coverage reflects growing public appetite for evidence-based explanations over sensationalized speculation. In an era of misinformation and conspiracy theories, the Baghdad battery case demonstrates that genuine mysteries can be solved through careful science, historical context, and respect for evidence. The story has particular resonance for science educators, who have incorporated the findings into curricula about the nature of scientific inquiry, the importance of empirical evidence, and the value of understanding technologies within their historical contexts. Students learning about the Baghdad battery now encounter not a tantalizing unsolved mystery, but a case study in how science works, how hypotheses are tested, how evidence is evaluated, how conclusions are reached through rigorous methodology. This educational value extends beyond archaeology into critical thinking skills applicable across disciplines. Perhaps the most profound lesson of the Baghdad battery discovery is about humility, both scientific humility and cultural humility. Scientific humility requires us to acknowledge the limits of our knowledge and remain open to evidence that challenges our assumptions. For decades, mainstream archaeologists dismissed the battery hypothesis partly because it didn't fit established narratives about ancient technological capabilities. Alternative theorists embraced the battery hypothesis partly because it supported their narratives about lost civilizations or alien intervention. Both approaches suffered from confirmation bias, the tendency to interpret evidence in ways that confirm pre-existing beliefs. The March Yıkımcı findings demonstrate the importance of approaching evidence without predetermined conclusions, of following the data wherever it leads even when it challenges established narratives. Cultural humility requires us to understand ancient peoples on their own terms, rather than judging them by modern standards. The Parthians weren't primitive failures who stumbled upon electricity by accident, nor were they recipients of alien technology who lost their way. They were skilled artisans who developed sophisticated solutions to practical problems within their cultural and technological contexts. Recognizing this requires us to set aside modern assumptions about what constitutes advanced technology and appreciate the genuine achievements of ancient peoples without either condescension or exaggeration. The Baghdad battery wasn't a failed attempt to create modern electrical technology. It was a successful solution to a specific metallurgical challenge. Understanding this difference is crucial for appreciating the diversity and sophistication of human technological achievement throughout history. Esther Chen reflected in the team's final report, the Baghdad battery teaches us that ancient peoples were neither primitive nor superhuman. They were practical problem solvers who developed elegant solutions using the materials and knowledge available to them. They didn't need aliens or lost civilizations to achieve remarkable things. They needed curiosity, observation, and craftsmanship, qualities that define humanity across all eras. The real mystery wasn't how ancient Mesopotamians created electrical batteries. The real mystery was why we found it so hard to believe they could develop sophisticated technologies on their own terms. Solving that mystery required not just scientific analysis, but a fundamental shift in how we approach the past. We had to stop asking what ancient peoples lacked compared to us, and start asking what they achieved with what they had. The answer, as it turns out, is far more impressive than any conspiracy theory. The shift in perspective from deficiency to achievement, from mystery to understanding, from speculation to evidence, represents the true value of the March Yikmung discovery. It's not just about solving a 90-year-old archaeological puzzle. It's about demonstrating how careful science, historical context, and cultural understanding can transform our relationship with the past. The Baghdad battery is no longer a symbol of lost super science or alien intervention. It's a testament to human ingenuity, ancient and modern, Parthian and contemporary, artisan and scientist. And in that transformation lays its greatest significance. The scientific community's response to the March Yikmung Baghdad battery findings was swift and overwhelmingly positive, a rare consensus in a field often characterized by vigorous debate and competing interpretations. Within 48 hours of the Metropolitan Museum team's press release, major archaeological institutions worldwide issued statements supporting the electrochemical gilding hypothesis. The British Museum confirmed that residue analysis of their own Baghdad battery replica matched the Metropolitan's findings. The Louvre announced plans to re-examine their Parthian silver collection using the team's methodology. The Art Museum in Baghdad, which houses the original artifact discovered by Wilhelm Knig in Muntorgesalta, issued a statement expressing pride that an Iraqi archaeological discovery had finally been understood through international scientific collaboration. Perhaps most significantly, the Journal of Archaeological Science fast-tracked publication of the team's complete findings, with peer reviewers unanimously praising the study's methodological rigor and historical contextualization. Elena Vasquez, editor-in-chief of the journal, and a leading authority on ancient metallurgy, wrote in her editorial introduction, "This study represents a model for how to resolve long-standing archaeological mysteries, not through sensationalism or speculation, but through careful experimentation, historical context, and respect for ancient craftsmanship." The Baghdad battery case should become required reading for archaeology students worldwide as an example of scientific methodology applied to historical interpretation. The consensus extended beyond archaeology into materials science and the history of technology. Michael Reynolds, director of the Materials Research Laboratory at the University of Illinois and author of the definitive textbook, Ancient Metallurgy, From Empirical Practice to Theoretical Understanding, called the findings transformative for understanding technological development. What's remarkable about this discovery, Reynolds explained in an interview with Science magazine, is that it demonstrates how sophisticated empirical knowledge can exist without theoretical frameworks. The Parthians didn't understand electron theory or electrochemical potentials. They didn't need to. They observed that certain material combinations produced predictable results, refined those combinations through trial and error, and applied them to solve practical problems. This is technology in its purest form, practical problem solving without theoretical baggage. It challenges our modern assumption that theoretical understanding must precede practical application. In many cases throughout history, the reverse has been true. Practical knowledge came first, theoretical understanding followed centuries or millennia later. Reynolds pointed to other examples. Roman concrete's superior durability wasn't understood theoretically until Yikmung, when researchers discovered the chemical reactions that made it stronger over time. Medieval stained glass artisans created vibrant colors through empirical knowledge of metal oxides long before atomic theory explained why those colors appeared. The Baghdad battery represents another example of this pattern, sophisticated practical knowledge preceding theoretical understanding by nearly 2,000 years. This pattern of empirical knowledge preceding theoretical understanding has profound implications for how we view technological development throughout human history. For decades, historians of technology have operated under what's called the theoretical primacy model, the assumption that theoretical understanding must precede practical application. According to this model, technologies emerge from scientific discoveries. Volta understands electrical theory, then invents the battery. Faraday understands electromagnetic induction, then develops the electric motor. Einstein understands relativity, then enables nuclear power. This model places theoretical science at the center of technological progress, with practical applications flowing naturally from scientific discoveries. The Baghdad battery findings challenge this model by demonstrating that sophisticated technologies can emerge from empirical observation alone, without any theoretical understanding of the underlying principles. Parthian artisans didn't need to understand why iron, copper, acidic liquids, and gold salts produced beautiful gilding on silver. They only needed to know that the combination worked reliably. They refined the process through generations of trial and error, accumulating practical knowledge without developing theoretical frameworks. This empirical primacy model better explains technological development in many pre-modern societies, where practical knowledge accumulated through craft traditions long before scientific theories emerged to explain why those techniques worked. The distinction between empirical and theoretical knowledge isn't just academic, it has real-world implications for how we approach technological innovation today. In our modern era of rapid scientific advancement, we often assume that theoretical understanding must precede practical application. We invest billions in basic research expecting practical applications to follow naturally. We prioritize theoretical knowledge over craft knowledge in our educational systems. We celebrate scientific discoveries while undervaluing practical craftsmanship. The Baghdad battery case reminds us that this hierarchy isn't universal or inevitable. Throughout most of human history, technological progress emerged from practical experimentation, craft traditions, and empirical observation, not from theoretical science. The Industrial Revolution itself relied heavily on empirical knowledge. James Watt improved the steam engine through practical experimentation, not theoretical thermodynamics, which emerged decades later. The Wright brothers achieved powered flight through wind tunnel testing in practical experimentation, not aerodynamic theory, which was still in its infancy. Even today, many technological breakthroughs emerge from practical tinkering rather than theoretical research. The Baghdad battery findings invite us to reconsider the relationship between theory and practice, to value empirical knowledge alongside theoretical understanding, and to recognize that technological innovation can emerge from multiple pathways, not just from scientific laboratories. This reconsideration has already begun influencing contemporary technological development. Following publication of the March Yikmung findings, several material science laboratories launched research programs exploring empirical-first approaches to materials development. At MIT's Materials Processing Center, Drlisa Chin initiated a project called Ancient Wisdom, Modern Materials, which systematically tests material combinations described in ancient craft manuals to discover properties that modern theory might have overlooked. We become so theory-driven that we sometimes miss simple solutions hiding in plain sight, Chen explained. Ancient artisans experimented with material combinations for centuries without theoretical constraints. They discovered things we might never think to because our theories tell us they shouldn't work. By systematically testing these ancient combinations, we're discovering new material properties and applications. One example, Chen's team tested a copper-zinc alloy described in a Roman metallurgical text as producing unusually strong bronze. Modern theory suggested the alloy should be brittle, but practical testing revealed it had exceptional fatigue resistance properties now being applied to aerospace components. Similarly, researchers at Stanford's biomimetics laboratory are studying ancient textile techniques described in Mesopotamian and Egyptian texts, discovering weaving patterns that produce materials with properties modern engineering hadn't considered. The Baghdad battery case has become a touchstone for these efforts, a reminder that empirical knowledge accumulated over centuries can complement theoretical understanding in unexpected ways. The educational implications of this shift are equally significant. For decades, science education has emphasized theoretical understanding over practical experimentation. Students learn scientific principles first, then apply them to practical problems. This approach has produced remarkable advances in theoretical knowledge, but it has also created a generation of scientists and engineers who sometimes struggle with hands-on problem solving. The Baghdad battery case demonstrates the value of reversing the sequence, starting with practical problems, and allowing theoretical understanding to emerge from experimentation. Several universities have already begun incorporating this approach into their curricula. At Columbia University, Robert Chin, who led the Metropolitan Museum team, developed a new course called Archaeological Problem Solving, From Ancient Craft to Modern Science, which challenges students to solve practical problems using only materials and knowledge available to ancient peoples. Students attempting to recreate electrochemical gilding without modern equipment discover first the empirical knowledge required to make the process work, knowledge that theoretical textbooks often overlook. Students who take this course develop a deeper appreciation for both ancient craftsmanship and modern science, Chen explains. They learn that theoretical understanding and practical knowledge aren't opposites, they're complementary. Ancient artisans developed sophisticated empirical knowledge through generations of experimentation. Modern scientists develop theoretical frameworks to explain why those techniques work. Both approaches are valuable. Both are necessary for complete understanding. This complementary relationship between ancient empirical knowledge and modern theoretical understanding has become particularly evident in conservation science, the field dedicated to preserving and restoring ancient artifacts. Following the March to findings, conservation laboratories worldwide begin applying electrochemical gilding techniques to restore damaged Parthian silver artifacts. At the British Museum's Conservation Laboratory, Dr. Thompson led a team that successfully restored a severely tarnished Parthian ritual bowl using the exact methods described in the cuneiform texts discovered by Dr. Wilson. The traditional approach to restoring gilded silver involved removing the damaged gilding and applying new gold using modern electroplating techniques, Thompson explained. But this often altered the artifact's appearance and destroyed historical evidence. Using the ancient electrochemical gilding technique, we can restore the original appearance while preserving the artifact's historical integrity. More importantly, we can match the exact thickness and distribution of the original gilding, something modern techniques couldn't achieve. The success of this approach has led to a broader reevaluation of conservation practice. Rather than automatically applying modern techniques to ancient artifacts, conservators are increasingly studying ancient manufacturing methods to develop restoration approaches that honor the original craftsmanship. This ancient methods for ancient artifacts philosophy has produced remarkable results, not just for Parthian silver, but for Roman glass, Egyptian papyrus, and Chinese porcelain. The Baghdad battery case has become a catalyst for the shift, demonstrating that understanding ancient technologies isn't just about historical curiosity, it has practical applications for preserving our cultural heritage. The public's response to these developments has been equally transformative. For decades, the Baghdad battery occupied a peculiar space in popular culture, simultaneously dismissed by mainstream archaeology as a mundane artifact and celebrated by alternative theorists as evidence of lost super science. This polarization created a false dichotomy: either the artifact was unimportant or it was revolutionary. The March findings resolved this dichotomy by demonstrating that the artifact was both important and explicable within established historical frameworks. Social media response reflected this resolution. On platforms like Twitter and Reddit, discussions shifted from "was this an ancient battery?" to "how did ancient artisans develop this technique, and what other ancient technologies might we be misunderstanding?" This shift represents a maturation in public engagement with archaeology, a move away from sensationalism toward genuine curiosity about how ancient people solve practical problems. Educational content creators have embraced this shift. YouTube channels like History March, Feature History, and Kings and Generals produce detailed videos explaining the March findings, emphasizing the scientific methodology and historical context rather than sensational implications. These videos have garnered millions of views, with comment sections filled with thoughtful discussions about ancient metallurgy, archaeological methodology, and the nature of technological development. The Baghdad battery is no longer a symbol of mystery or conspiracy, it's become a case study in how science works. This transformation has particular significance for science communication in an era of misinformation and conspiracy theories. For decades, the Baghdad battery was weaponized by proponents of ancient astronaut theories to suggest that mainstream archaeology was hiding evidence of advanced prehistoric technologies. The March findings demonstrate the opposite. Archaeology's strength lays in its willingness to follow evidence wherever it leads, even when that evidence challenges established narratives. The Metropolitan Museum team didn't set out to debunk conspiracy theories, they set out to answer a genuine historical question using rigorous scientific methods. Their conclusion, that the vessels were electrochemical gilding tools, actually elevates ancient Mesopotamian achievement rather than diminishing it. It reveals a level of chemical sophistication previously unrecognized in Parthian craftsmanship. This approach, focusing on evidence rather than ideology, on understanding rather than debunking, has proven remarkably effective at countering misinformation. When conspiracy theorists claim the findings are a cover-up, science communicators can point to the transparent methodology, peer-reviewed publications, and international consensus. When alternative theorists suggest the team missed something, educators can explain the multiple lines of evidence supporting the conclusion. The Baghdad battery case has become a model for how to address pseudo-scientific claims, not by attacking believers, but by demonstrating the power of evidence-based inquiry. The philosophical implications of this case study extend beyond archaeology and science communication into fundamental questions about human knowledge and technological development. The Baghdad battery findings challenge what philosopher Thomas Kuhn called paradigm blindness, the tendency to interpret evidence through established theoretical frameworks while missing alternative explanations. For decades, archaeologists viewed the Baghdad battery through the paradigm of modern electrical technology, asking whether it functioned as a battery in the contemporary sense. This question framed the artifact as either a primitive failed attempt at modern technology or evidence of lost super science. Both interpretations were wrong because they imposed modern categories on ancient objects. The March Yıkımın team succeeded by stepping outside this paradigm by asking not, was this a battery, but what problem did this solve for the people who made it? The shift in questioning opened the door to understanding the artifact on its own terms, rather than forcing it into modern categories. This approach has profound implications for how we approach other historical mysteries and contemporary problems. Many of our most challenging problems, from climate change to social inequality, resist solution because we frame them through established paradigms that limit our thinking. The Baghdad battery case reminds us that sometimes the most powerful innovation comes not from better answers, but from better questions. By asking what ancient peoples were trying to achieve rather than what modern categories their artifacts fit into, the Metropolitan Museum team unlocked understanding that had eluded scholars for 90 years. This lesson in questioning has already begun influencing other fields. In medicine, researchers studying traditional healing practices are shifting from "does this work" to "what problem is this practice trying to solve?" This approach has led to discoveries of effective treatments hidden within traditional knowledge systems, treatments that modern medicine had dismissed because they didn't fit established paradigms. In environmental science, researchers studying indigenous land management practices are asking not, is this scientific, but what ecological problem does this practice address? This approach has revealed sophisticated ecological knowledge embedded in traditional practice, knowledge that modern conservation science is now incorporating into management strategies. The Baghdad battery case has become a touchstone for this methodological shift, a reminder that understanding requires empathy, context, and willingness to step outside established frameworks. Esther Chen reflected in a keynote address at the Yıkımın Society for American Archaeology Conference, the Baghdad battery taught us that the most powerful tool in archaeology isn't ground-penetrating radar or carbon dating or DNA analysis. It's the ability to ask better questions. For 90 years, we asked the wrong question: was this a battery? The right question was, what problem did this solve? That question led us to understanding. It led us to appreciation. It led us to recognition of ancient achievement on its own terms. That's the real discovery, not what the artifact was, but how we learned to see it. This recognition of ancient achievement on its own terms represents perhaps the most profound impact of the March Yıkımın findings. For decades, discussions of ancient technologies have been trapped in a binary. Either ancient peoples were primitive and incapable of sophisticated achievement, or they possessed lost super science or alien existence. Both perspectives are condescending, they deny ancient people's agency and intelligence. The Baghdad battery findings offer a third way: ancient peoples were neither primitive nor superhuman. They were practical problem solvers who developed sophisticated solutions using the materials and knowledge available to them. They didn't need aliens or lost civilizations to achieve remarkable things. They needed curiosity, observation, and craftsmanship, qualities that define humanity across all eras. This perspective doesn't diminish ancient achievement, it contextualizes it authentically. It recognizes that technological sophistication isn't about matching modern capabilities, but about solving problems effectively within historical constraints. The Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding this difference is crucial for appreciating the diversity and sophistication of human technological achievement throughout history. The legacy of the Baghdad battery discovery will extend far beyond archaeology. It has already begun influencing how we think about technology, knowledge, and human achievement. It has demonstrated that empirical knowledge accumulated over centuries can complement theoretical understanding in unexpected ways. It has shown that practical problem solving can produce sophisticated technologies without theoretical frameworks. It has reminded us that understanding requires empathy, context, and willingness to step outside established paradigms. Most importantly, it has restored agency and intelligence to ancient peoples, recognizing them not as primitive failures or recipients of alien technology, but as skilled artisans who developed elegant solutions to practical problems. As museums worldwide update their exhibits to reflect the March Yıkımın findings, visitors will encounter not a mysterious artifact labeled ancient battery, but a sophisticated tool labeled Parthian electrochemical gilding cell with explanations of how it worked, why it was developed, and what it reveals about ancient Mesopotamian craftsmanship. The shift from mystery to understanding, from speculation to evidence, from condescension to appreciation represents the true value of the discovery. The Baghdad battery is no longer a symbol of what we don't know about the past. It's a testament to what we can learn when we approach the past with curiosity, respect, and willingness to ask better questions. And in that transformation lies its greatest significance, not just for archaeology, but for how we understand human achievement across all eras. The March to Baghdad battery discovery triggered a quiet revolution across the world's museums, a systematic re-examination of artifacts previously dismissed as ritual objects or storage containers that might actually represent sophisticated ancient technologies misunderstood through modern lenses. Within weeks of the Metropolitan Museum's publication, curatorial teams at major institutions began applying the team's methodology to their own collections. At the British Museum, conservators re-examined a collection of 12 similar clay vessels from Seleucia on the Tigris, previously catalogued as unidentified ritual containers. Using non-invasive X-ray fluorescence scanning, they discovered copper and iron residues inside 8 vessels matching the Baghdad battery configuration. More significantly, residue analysis revealed microscopic gold particles embedded in the bitumen seals of 3 vessels, identical to the evidence found in the Metropolitan's original artifact. The British Museum immediately reclassified these objects as Parthian electrochemical gilding cells and updated their online catalogue with detailed explanations of the March findings. Similar reclassifications occurred at the Louvre, the Vorderasiatisches Museum in Berlin, and the Arak Museum in Baghdad, each institution discovering previously overlooked evidence supporting the electrochemical gilding hypothesis. This global reassessment revealed a striking pattern. Vessels matching the Baghdad battery configuration have been found at 27 archaeological sites across Mesopotamia, all dating between Juzbas and Yukuzusi, all associated with religious or elite contexts, and all showing evidence of singly used destruction consistent with the gilding process. The artifacts weren't anomalies, they represented a widespread, standardized technology used across the Parthian Empire for producing ritual objects. This reassessment extended beyond Mesopotamia to other ancient civilizations previously thought incapable of electrochemical knowledge. At the Egyptian Museum in Cairo, researchers re-examined a collection of vessels from the Ptolemaic period that had puzzled archaeologists for decades. These vessels, clay containers with copper linings and iron rods, had been dismissed as unidentified ritual objects with no clear function. Applying the Metropolitan Museum's methodology, Egyptian conservators discovered that several vessels contained residues of malachite powder, copper carbonate, and vinegar, components that would create an electrolyte solution capable of electrochemical deposition. More remarkably, analysis of gilded artifacts from the same period revealed gold layers with microscopic characteristics matching electrochemical deposition rather than fire gilding. This suggested that electrochemical gilding technique may have spread from Mesopotamia to Egypt through Hellenistic trade networks following Alexander the Great's conquests, a transmission of practical knowledge that left few written records, but clear material evidence. Similar reassessments occurred in India, where researchers at the National Museum in New Delhi examined copper-iron artifacts from the Mauryan period, previously considered ritual objects. While conclusive evidence remains elusive, preliminary analysis suggests possible electrochemical applications in early Indian metallurgy, a finding that could rewrite understanding of technological exchange along ancient trade routes connecting Mesopotamia, Egypt, and the Indian subcontinent. These discoveries demonstrate that the Baghdad battery wasn't an isolated curiosity but part of a broader pattern of sophisticated empirical knowledge that spread across the ancient world through trade, migration, and cultural exchange, knowledge that modern archaeology had systematically overlooked because it didn't fit established categories of technology. The role of modern technology in enabling these discoveries cannot be overstated. The March breakthrough relied on an analytical technique was unavailable to Wilhelm or even to researchers in the JIPS. Mass spectrometry allowed Mitchell to detect gold particles at concentrations of parts per billion impossible to see with the naked eye or even under standard microscopes. Scanning electron microscopy revealed microscopic surface characteristics distinguishing electrochemical gilding from fire gilding, differences invisible to earlier researchers. Most significantly, artificial intelligence played a crucial role in connecting disparate pieces of evidence. The Metropolitan Museum team employed a machine learning algorithm called ArtifactNet, developed specifically for cross-referencing archaeological databases worldwide, to identify patterns across thousands of artifacts that human researchers might miss. ArtifactNet analyzed descriptions, images, and analytical data from over 50,000 Mesopotamian artifacts in global museum collections, identifying 23 vessels matching the Baghdad battery configuration that had been misclassified under vague descriptions like ceramic container with metal fittings or unidentified ritual object. The algorithm also identified correlations between these vessels and gilded silver artifacts from the same sites and periods, correlations that suggested functional relationships invisible to traditional archaeological analyses. When the team cross-referenced these findings with textual databases containing translations of cuneiform tablets, ArtifactNet identified 17 previously overlooked references to vine acid gilding in administrative records, texts that human researchers had dismissed as references to conventional techniques. This synergy between human expertise and artificial intelligence represents a new frontier in archaeological research, a frontier where algorithms don't replace archaeologists, but augment their ability to see patterns across vast datasets. As Durchin noted in the team's final report, ArtifactNet didn't solve the mystery. It gave us better questions. It showed us where to look, what connections to investigate, which artifacts deserved closer examination. The real discovery still required human expertise, contextual understanding, historical knowledge, craft experience. But it helped us see the forest when we'd been staring at individual trees for 90 years. This technological synergy has already begun transforming archaeological practice worldwide. Following the Baghdad battery success, major museums have launched collaborative initiatives combining traditional archaeological expertise with advanced analytical technologies and artificial intelligence. The Global Artifact Intelligence Project, launched in April by a consortium including the Metropolitan Museum, the British Museum, the Louvre, and the Arak Museum, aims to apply this methodology to 50,000 unidentified or poorly understood artifacts in their collections. The project's first phase focuses on metallurgical artifacts from the ancient Near East, with initial results already revealing previously unrecognized technological patterns. At the Arak Museum, Iraqi archaeologists are using portable X-ray fluorescence scanners, donated by the Metropolitan Museum as part of a cultural heritage partnership, to analyze artifacts still in Iraqi soil before excavation. This non-invasive approach allows researchers to identify promising artifacts without removing them from their archaeological context, preserving valuable stratigraphic information. The partnership also includes training programs for Iraqi conservators in advanced analytical techniques, a crucial step toward building sustainable archaeological capacity in Iraq after decades of conflict and looting. This emphasis on collaboration with source countries represents a significant ethical shift in archaeological practice. For decades, Western museums held artifacts like the Baghdad battery while Iraqi scholars had limited access to study them. The Malta project reversed this dynamic. The Metropolitan Museum team worked closely with Iraqi archaeologists from the Arak Museum, sharing data in real time, co-authoring publications, and ensuring Iraqi scholars received equal credit for the discovery. Jalala Hassan, head of conservation at the Arak Museum, and co-author of the March Malta publication, emphasized this partnership's importance. For 90 years, this artifact discovered on Iraqi soil was studied primarily by Western scholars who often dismissed its significance or sensationalized it with alien theories. The Malta project finally centered Iraqi expertise, or knowledge of Mesopotamian languages, or understanding of local craft traditions, or connection to this heritage. The discovery belongs to humanity, but its interpretation must honor the people whose ancestors created it. This partnership model should become standard practice, not exceptional. This ethical dimension extends to ongoing debates about artifact repatriation, the return of cultural objects to their countries of origin. The Baghdad battery itself remains in the Arak Museum in Baghdad, where it has been since Alta discovery. Unlike many Mesopotamian artifacts held in Western museums, it was never removed from Arak, a fact that shaped the Malta research dynamic. The Metropolitan Museum team traveled to Baghdad to study the original artifact, rather than requesting its loan, conducting their residue analysis on site with Iraqi conservators. This approach respected Iraqi sovereignty over cultural heritage while enabling international collaboration. The success of this model has influenced broader repatriation discussions. In May Malta, the British Museum announced it would return 17 artifacts to Arak that had been looted during the conflict, artifacts whose provenance had been unclear until advanced imaging techniques matched them to specific excavation sites. The announcement cited the Baghdad battery collaboration as demonstrating that ethical stewardship of cultural heritage requires respecting source nations' sovereignty while enabling international scholarly access through partnership rather than possession. Similarly, the Louvre announced a 5-year loan program allowing Iraqi museums to display French-held Mesopotamian artifacts in Baghdad, with French conservators training Iraqi colleagues in preservation techniques during the loan period. These developments represent a gradual shift away from colonial-era practice of artifact acquisition toward models emphasizing partnership, capacity building, and shared stewardship. The Baghdad battery case demonstrates that ethical collaboration doesn't diminish research quality, it enhances it by centering local expertise and contextual knowledge essential for accurate interpretation. The discovery's implications for understanding other, mysterious, ancient artifacts have proven equally transformative. Following publication of the March Yikmung findings, researchers began re-examining artifacts previously dismissed as anomalous or explained away through speculative theories. At the National Archaeological Museum in Athens, conservators re-examined the Antikythera mechanism, not to suggest it was alien technology, but to better understand the sophisticated astronomical knowledge and mechanical engineering of Hellenistic Greece within its proper historical context. Their analysis confirmed that the mechanism's complexity reflected established Greek mathematical traditions rather than lost super science, a conclusion that actually elevates Greek achievement by demonstrating its continuity with earlier Babylonian astronomy and later Islamic engineering. Similarly, researchers at the Egyptian Museum re-examined the so-called Dendera light bulbs carvings in the Hathor Temple at Dendera that alternative theorists claimed depicted ancient electrical lighting. Mainstream Egyptologists have long argued these carvings represent symbolic lotus flowers and snakes within Egyptian religious iconography. The Baghdad battery findings provide additional support for this interpretation by demonstrating that when ancient peoples developed electrical phenomena, they applied them to practical metallurgical purposes, not lighting systems. The absence of any archaeological evidence for ancient electrical lighting, wires, generators, bulbs, alongside the presence of clear evidence for electrochemical gilding suggests ancient peoples understood and applied electrochemical principles selectively based on practical needs. This contextual understanding helps debunk pseudo-scientific claims while simultaneously elevating genuine ancient achievements, recognizing that sophisticated empirical knowledge doesn't require theoretical frameworks matching modern science. Perhaps most significantly, the Baghdad battery case has transformed how archaeologists approach artifacts that don't fit established categories. For decades, archaeologists faced a false choice when encountering anomalous objects: either force them into existing categories, dismissing evidence that didn't fit, or sensationalize them as evidence of lost civilizations or alien intervention. The March Yikmung findings demonstrated a third path: developing new categories based on evidence rather than forcing artifacts into pre-existing frameworks. This approach requires intellectual humility, the willingness to acknowledge when our categories are inadequate and develop new frameworks based on material evidence. It also requires contextual understanding, the ability to interpret artifacts within their historical, cultural, and technological contexts rather than judging them by modern standards. Following the Baghdad battery success, the Society for American Archaeology issued new guidelines for interpreting anomalous artifacts, emphasizing 3 principles. First, prioritize material evidence over theoretical expectations. Second, seek functional explanations within historical contexts before invoking extraordinary claims. Third, collaborate with specialists from multiple disciplines to develop comprehensive interpretations. These guidelines have already influenced archaeological practice worldwide. In June Yikmung, a team excavating a Roman site in Britain discovered ceramic vessels with copper fittings that initially puzzled researchers. Rather than dismissing them as ritual objects or speculating about Roman batteries, the team applied the Baghdad battery methodology, conducting residue analysis, testing functional hypotheses, and consulting metallurgical specialists. They discovered the vessels were used for electrochemical purification of silver, a technique previously unknown in Roman Britain but consistent with Roman metallurgical knowledge transmitted through trade networks. The discovery didn't rewrite history with alien intervention, it enriched understanding of Roman technological adaptation and cultural exchange. This evidence-based approach represents archaeology's greatest strength, the willingness to follow evidence wherever it leads while maintaining rigorous standards of proof. The educational impact of this methodological shift extends beyond professional archaeology into public understanding of science and history. Following the March Yikmung findings, the Metropolitan Museum launched a digital exhibit titled "Solving Ancient Mysteries." The Baghdad battery case study, which walks visitors through the entire investigative process from initial observation to hypothesis testing to conclusion. The exhibit emphasizes not just what was discovered, but how it was discovered, the methodologies, the dead ends, the collaborative process. Visitors can interact with virtual replicas of the battery, different electrolyte solutions, and see microscopic comparisons between electrochemical and fire gilding. The exhibit has become one of the museum's most popular educational resources, with over 2 million online visitors in its first month. Teachers worldwide have incorporated it into science and history curricula, using it to teach critical thinking, scientific methodology, and the nature of evidence. As Dr. Mitchell explained in an interview about the exhibit, we wanted to show that science isn't about having all the answers, it's about asking better questions. The Baghdad battery wasn't solved by a eureka moment. It was solved by systematic testing, collaboration across disciplines, willingness to revise hypotheses based on evidence, and respect for insane craftsmanship. These are skills that matter far beyond archaeology. They're essential for navigating our complex world. This emphasis on process over product has proven particularly valuable in an era of misinformation, demonstrating how evidence-based inquiry can resolve genuine mysteries without resorting to conspiracy theories or sensationalism. The Baghdad battery case has also influenced science communication practices beyond archaeology. Following the Yukmung-Jirmalta findings, major science media outlets adopted new guidelines for covering archaeological discoveries, emphasizing methodological rigor over sensational claims, providing historical context alongside new findings, and distinguishing clearly between evidence and speculation. National Geographic's revised style guide now requires writers to answer 3 questions before publishing archaeological claims. What is the material evidence? How was it analyzed? What alternative explanations were considered and why were they rejected? These guidelines have significantly improved archaeological coverage, reducing sensationalism while increasing public understanding of how archaeological knowledge is constructed. The shift reflects growing recognition that responsible science communication requires not just reporting discoveries, but explaining how those discoveries were made, making the scientific process transparent and accessible. As science journalist Jermea Rodriguez noted in a Columbia Journalism Review article, the Baghdad battery coverage marked a turning point. For the first time, major outlets explained not just what was discovered, but how walking readers through residue analysis, comparative metallurgy, textual interpretation. This transparency built public trust while demonstrating science's self-correcting nature. Readers saw archaeology not as a collection of facts, but as a dynamic process of inquiry. That's a more accurate and more inspiring portrait of science. This transparency has proven particularly valuable for countering pseudo-scientific claims. When conspiracy theorists inevitably claimed the March Yukmung-Jirmalta findings were a cover-up hiding alien technology, science communicators could point to the transparent methodology, peer-reviewed publications, and international consensus. The Metropolitan Museum team made all their data publicly available, including raw spectrometry readings, microscopic images, and experimental protocols, allowing independent verification. When alternative theorists suggested the team missed evidence of higher voltage applications, educators could explain why multiple vessels couldn't be connected in series, no archaeological evidence of wires or connectors, and why even connected vessels couldn't produce useful voltage, maximum 20 volts insufficient for lighting or machinery. This evidence-based approach proved remarkably effective at countering misinformation, not by attacking believers, but by demonstrating the power of transparent methodology. Esther Chen observed, conspiracy theories thrive in information vacuums. When we make our methods transparent, showing exactly how we reached our conclusions, we remove the vacuum. People might still choose to believe alternative narratives, but they can't claim we're hiding evidence. Transparency doesn't eliminate conspiracy theories, but it does inoculate the public against their most pernicious forms. The philosophical implications of this case study extend into fundamental questions about knowledge production and cultural interpretation. The Baghdad battery findings demonstrate that understanding requires not just analytical tools, but empathetic imagination, the ability to see artifacts through the eyes of their creators rather than imposing our categories upon them. For 90 years, scholars asked whether the vessel was a battery in the modern sense, a question that framed the artifact through 1st century European electrical theory rather than 2nd century Mesopotamian craft knowledge. The breakthrough came when researchers asked what problem the vessel solved for Parthian artisans, a question requiring empathy with insight priorities, values, and constraints. This empathetic approach doesn't mean abandoning scientific rigor, it means complementing analytical methods with contextual understanding. It recognized that artifacts are not neutral objects, but material expressions of human intention, objects created to solve specific problems within specific cultural contexts. Understanding those intentions requires both scientific analysis and historical imagination. As anthropologist Dr. James Wilson reflected in the team's final report, we spent 90 years analyzing what the Baghdad battery was: a vessel, a cylinder, a rod, bitumen. We finally understood it when we asked what it did: solved a metallurgical problem for Parthian artisans creating ritual objects. The shift from ontology to function, from object to action, transformed mystery into understanding. This shift matters far beyond archaeology. It reminds us that understanding any human creation, ancient or modern, requires seeing it not as a static object, but as a solution to a problem, an expression of intention, a response to context. This insight has already begun influencing fields beyond archaeology. In design thinking, practitioners are adopting problem-first approaches inspired by the Baghdad battery case, studying objects not as finished products, but as solutions to specific problems within specific contexts. At Stanford's school, instructors use the Baghdad battery as a case study in empathetic design, challenging students to understand user needs before proposing solutions. In artificial intelligence development, researchers are exploring context-aware algorithms that interpret data within cultural and historical frameworks rather than imposing universal categories, an approach directly inspired by the Baghdad battery methodology. Even in conflict resolution, mediators are applying problem-first approaches, seeking to understand underlying needs rather than negotiating over positions, a methodology showing the shift from "was this a battery" to "what problem did this solve?" The Baghdad battery case has become a touchstone for this methodological shift across disciplines, a reminder that understanding requires both analytical rigor and empathetic imagination, both scientific method and historical context. As museums worldwide update their exhibits to reflect the March Malta findings, visitors encounter not a mysterious artifact labeled ancient battery, but a sophisticated tool labeled Parthian electrochemical gilding cell with explanations of how it worked, why it was developed, and what it reveals about ancient Mesopotamian craftsmanship. The shift from mystery to understanding, from speculation to evidence, from condescension to appreciation represents the discovery's true value. The Baghdad battery is no longer a symbol of what we don't know about the past. It's a testament to what we can learn when we approach the past with curiosity, respect, and willingness to ask better questions. And in that transformation lies its greatest significance, not just for archaeology, but for how we understand human achievement across all eras. The vessels and museum cases worldwide now tell a richer story, not of alien intervention or lost super science, but of human ingenuity, Parthian artisans observing material interactions, refining techniques through generations of experimentation, solving practical problems with elegant chemistry. This story doesn't diminish ancient achievement, it contextualizes it authentically. It recognizes that technological sophistication isn't about matching modern capabilities, but about solving problems effectively within historical constraints. The Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding this difference is crucial for appreciating the diversity and sophistication of human technological achievement throughout history. The Baghdad battery's legacy will be measured not in volts or amperes, but in changed perspectives, in our ability to see ancient peoples not as primitive failures or recipients of alien technology, but as skilled problem solvers whose achievements deserve recognition on their own terms. That recognition is the real discovery, and it belongs not to any single museum or nation, but to all of humanity. On the morning of March 15, Malta, as Dr. Mitchell prepared the final press release summarizing the Metropolitan Museum team's findings, she reflected on the journey that had brought them to this moment. 90 years of speculation, controversy, and misunderstanding were finally giving way to understanding, not through dramatic revelation or sensational discovery, but through careful science, historical context, and respect for ancient craftsmanship. The Baghdad battery was no longer a symbol of mystery or conspiracy. It was a testament to human ingenuity, ancient and modern, Parthian and contemporary, artisan and scientist. As Mitchell typed the final words of the press release, she realized the discovery's true significance wasn't about solving a 90-year-old puzzle. It was about demonstrating how genuine understanding emerges when we approach the past with curiosity rather than preconceptions, with evidence rather than ideology, with respect rather than condescension. This realization would shape not just how museums displayed the artifact, but how generations of students, researchers, and curious minds would understand the relationship between ancient peoples and modern science. The Baghdad battery case had become more than an archaeological discovery, it had become a methodology, a philosophy, a model for how to engage with the past in ways that honor both historical truth and human achievement. The scientific consensus that emerged in the months following March Malta represented one of archaeology's most remarkable transformations, from polarization to unity, from speculation to evidence, from mystery to understanding. Within 6 months of publication, every major archaeological institution worldwide had updated their interpretations of similar artifacts. Textbooks were revised. Museum exhibits redesigned. Academic curricula transformed. The Journal of Archaeological Science dedicated its September 2026 issue entirely to the Baghdad Battery Paradigm Shift, featuring 23 peer-reviewed papers from researchers across 5 continents examining implications for metallurgy, craft traditions, technological transmission, and archaeological methodology. Perhaps most significantly, the consensus extended beyond archaeology into public understanding. A Pew Research Center survey conducted in October 2026 found that 60% of Americans correctly identified the Baghdad battery as an ancient tool for gilding metal objects, a dramatic shift from 2015, when only 20% could correctly identify its purpose, with 30% believing it was evidence of ancient electrical technology, and 40% dismissing it as just a storage jar. This transformation in public understanding didn't happen through debunking or confrontation. It happened through transparent methodology, accessible explanation, and respect for both ancient achievement and modern science. The Baghdad battery case demonstrated that when we make the scientific process transparent, showing exactly how conclusions were reached, what evidence was considered, what alternatives were rejected, public trust follows naturally. This lesson has proven invaluable in an era of misinformation, demonstrating that evidence-based inquiry can resolve genuine mysteries without resorting to conspiracy theories or sensationalism. The educational legacy of the March 2026 findings has proven equally transformative. Across the United States, science and history teachers have incorporated the Baghdad battery case study into their curricula as a model of scientific methodology and critical thinking. The National Science Teaching Association developed a standardized lesson plan titled From Mystery to Understanding, the Baghdad battery case study, which guides students through the entire investigative process from initial observation to hypothesis testing to conclusion. Students learn not just what was discovered, but how it was discovered, the dead ends, the collaborative process, the willingness to revise hypotheses based on evidence. This emphasis on process over product has proven particularly valuable for developing critical thinking skills applicable far beyond archaeology. As high school science teacher Maria Rodriguez explained in an interview with Education Week, before the Baghdad battery case study, my students saw science as a collection of facts to memorize. Now they see it as a dynamic process of inquiry. They understand that genuine discovery requires patience, collaboration, willingness to be wrong, and commitment to evidence. These aren't just scientific skills, they're life skills. The Baghdad battery taught my students that the most powerful discoveries often come not from having all the answers, but from asking better questions. This pedagogical shift has extended into higher education as well. Universities worldwide have developed interdisciplinary courses combining archaeology, materials science, history of technology, and science communication courses that use the Baghdad battery as a central case study in how different disciplines can collaborate to solve complex problems. At Columbia University, Dr. Robert Chin's course, Archaeological Problem Solving, has become one of the most popular offerings in the archaeology department, with students from engineering, chemistry, history, and anthropology working together to recreate ancient technologies using only period-appropriate materials and knowledge. This interdisciplinary approach reflects a broader recognition that complex problems, whether ancient mysteries or contemporary challenges, require collaboration across disciplinary boundaries. The ethical dimensions of the March 2026 research have also reshaped archaeological practice worldwide. The partnership between the Metropolitan Museum and the Art Museum, centering archaeological expertise, sharing data transparently, ensuring equal credit, has become a model for ethical collaboration in cultural heritage research. In November 2026, UNESCO adopted new guidelines for international archaeological partnerships, explicitly setting the Baghdad battery collaboration as demonstrating best practice in ethical stewardship of cultural heritage. The guidelines emphasize 3 principles. First, research must center expertise from source countries. Second, data must be shared transparently with all partners. Third, publications must ensure equal credit for all contributors regardless of institutional affiliation or geographic location. These guidelines have already influenced major archaeological projects worldwide. The Global Artifact Intelligence Project, launched in April 2026, has expanded to include partnerships with museums and research institutions in Egypt, India, China, Mexico, and Peru, each partnership following the Baghdad battery model of centering local expertise while enabling international collaboration. At the Art Museum, Dr. Layla Hassan has established a new center for Mesopotamian materials analysis, equipped with portable analytical instruments donated by partner institutions and staffed by Iraqi conservators trained through the partnership. The center has already analyzed over 500 artifacts still in Iraqi soil, identifying previously unrecognized technological patterns and training a new generation of Iraqi conservators in advanced analytical techniques. This capacity building represents perhaps the most significant ethical legacy of the March Yukmung-Jirmalta findings, not just solving a mystery, but empowering the people whose ancestors created the artifact to lead its interpretation and preservation. The technological implications of the discovery have proven equally far-reaching. The success of ArtifactNet, the machine learning algorithm developed specifically for the Baghdad battery research, has sparked a revolution in archaeological data analysis. Following the March Yukmung-Jirmalta publication, the Metropolitan Museum team open-sourced the ArtifactNet code, making it freely available to researchers worldwide. Within months, archaeologists across 5 continents had adapted the algorithm to their own research questions, identifying previously unrecognized patterns in ceramic typologies, tracing trade routes through material composition analysis, detecting subtle stylistic variations indicating workshop affiliations. At the University of Cambridge, researchers developed TextNet, an algorithm specifically designed to cross-reference archaeological findings with textual databases, identifying correlations between material artifacts and written records that human researchers might miss. TextNet's first major success came in December Yukmung-Jirmalta, when it identified 37 previously overlooked references to electrochemical gilding techniques in cuneiform tablets housed in the British Museum, references that had been dismissed as descriptions of conventional techniques, but that, when re-examined in light of the Baghdad battery findings, clearly described the electrochemical process. This synergy between human expertise and artificial intelligence has transformed archaeological research from a discipline limited by human capacity to process information into one augmented by computational power that doesn't replace human insight, but amplifies it, as Chen reflected in a keynote address at the Yukmung-Jirmalta International Conference on Archaeological Computing. ArtifactNet didn't solve the mystery. It gave us better questions. It showed us where to look, what connections to investigate, which artifacts deserved closer examination. The real discovery still required human expertise, contextual understanding, historical knowledge, craft experience. But it helped us see the forest when we'd been staring at individual trees for 90 years. This partnership between human insight and computational power represents archaeology's future, not replacement, but augmentation. This augmentation has already begun transforming conservation practice worldwide. Following the March Yukmung-Jirmalta findings, conservation laboratories have increasingly applied ancient manufacturing techniques to restore damaged artifacts, techniques that often preserve historical integrity better than modern methods. At the British Museum, Dr. Thompson's team has successfully restored over 24 Parthian silver artifacts using the exact electrochemical gilding technique was described in the cuneiform texts. The results have been remarkable, not just aesthetically, but historically. Unlike modern electroplating, which often alters an artifact's appearance and destroys historical evidence, the ancient technique matches the original gilding's thickness, distribution, and microscopic characteristics exactly. More importantly, it preserves the artifact's historical integrity, allowing future researchers to study the original manufacturing technique without interference from modern restoration methods. This ancient methods for ancient artifacts philosophy has extended beyond metallurgy to other conservation domains. At the Egyptian Museum in Cairo, conservators are applying ancient papyrus-making techniques to restore damaged scrolls. At the National Museum of China, researchers are using traditional silk weaving methods to repair ancient textiles. At the National Museum of Anthropology in Mexico City, conservators are employing Precolumbian ceramic techniques to restore broken pottery. The Baghdad battery case has become a catalyst for this broader shift, demonstrating that understanding ancient technologies isn't just about historical curiosity, but has practical applications for preserving our cultural heritage. As Dr. Thompson explained in a Yukmung-Jirmalta conservation conference, we used to think modern techniques were always superior. The Baghdad battery taught us that ancient artisans developed sophisticated solutions to practical problems, solutions that sometimes work better than our modern approaches for preserving their own artifacts. This isn't about rejecting modern science. It's about recognizing that ancient knowledge has value, and that the best conservation approaches often combine ancient wisdom with modern understanding. The philosophical implications of the March Yukmung-Jirmalta findings extend far beyond archaeology and conservation into fundamental questions about human knowledge, technological development, and our relationship with the past. The Baghdad battery case demonstrates that technological sophistication isn't about matching modern capabilities, it's about solving problems effectively within historical constraints. The Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding this difference is crucial for appreciating the diversity and sophistication of human technological achievement throughout history. This perspective challenges what historian David Edgerton calls the innovation-centric view of technology, the assumption that technological progress is linear, inevitable, and always oriented toward greater complexity and power. The Baghdad battery reveals a different pattern. Technologies emerge to solve specific problems within specific contexts, and their success is measured not by theoretical sophistication, but by practical effectiveness. This contextual understanding has profound implications for how we approach contemporary technological challenges. In an era of rapid technological change, we often assume that newer is always better, that complexity always represents progress, that theoretical understanding must precede practical application. The Baghdad battery reminds us that these assumptions aren't universal. Sometimes the most elegant solutions are simple. Sometimes practical knowledge precedes theoretical understanding. Sometimes the best technology for a specific problem isn't the most advanced, it's the most appropriate. This lesson has already begun influencing contemporary technological development. At MIT's Materials Processing Center, Drlisa Chen's Ancient Wisdom Modern Materials project has discovered new material properties by systematically testing combinations described in ancient craft manuals, combinations that modern theory had dismissed as impossible. At Stanford's biomimetics laboratory, researchers studying ancient textile techniques have discovered weaving patterns that produce materials with properties modern engineering hadn't considered. The Baghdad battery case has become a touchstone for these efforts, a reminder that empirical knowledge accumulated over centuries can complement theoretical understanding in unexpected ways. This complementarity between ancient empirical knowledge and modern theoretical understanding represents perhaps the discovery's most profound legacy. For decades, the history of science has been framed as a progression from superstition to rationality, from empirical observation to theoretical understanding, from craft knowledge to scientific knowledge. This narrative positions modern science as the pinnacle of human intellectual achievement, valuable, but also condescending to earlier forms of knowledge. The Baghdad battery findings challenge this narrative by demonstrating that empirical knowledge and theoretical understanding aren't opposites, they're complementary. Ancient artisans developed sophisticated practical knowledge through generations of experimentation. Modern scientists develop theoretical frameworks to explain why those techniques work. Both approaches are valuable. Both are necessary for complete understanding. This recognition has begun transforming how we teach the history of science and technology. Textbooks now present technological development not as a linear progression from primitive to advanced, but as a complex tapestry of empirical knowledge, theoretical understanding, cultural context, and practical problem solving. Students learn that Roman concrete's superior durability wasn't understood theoretically until but was developed empirically centuries earlier. They learn that medieval stained glass artisans created vibrant colors through empirical knowledge of metal oxides long before atomic theory explained why those colors appeared. They learn that Parthian artisans developed electrochemical gilding through observation and experimentation centuries before Volta understood electrical theory. This nuanced understanding helps students appreciate the diversity of human technological achievement without either romanticizing ancient peoples as primitive or inflating them with pseudo-scientific claims. It also helps students understand that technological development isn't linear or inevitable, it's shaped by cultural values, economic systems, environmental constraints, and historical contingencies. The Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding why technologies develop or don't develop in specific historical contexts is crucial for making sense of both the past and the present. The Baghdad battery's legacy will extend far beyond archaeology into how we understand human achievement across all eras. The artifact is no longer a symbol of mystery or conspiracy. It's a testament to human ingenuity, ancient and modern, Parthian and contemporary, artisan and scientist. It reminds us that genuine understanding emerges not from sensationalism or speculation, but from careful science, historical context, and respect for evidence. It demonstrates that ancient peoples were neither primitive failures nor recipients of alien technology, they were skilled problem solvers who developed elegant solutions using the materials and knowledge available to them. It shows that technological sophistication isn't about matching modern capabilities, but about solving problems effectively within historical constraints. Most importantly, it reveals that the most powerful discoveries often come not from having all the answers, but from asking better questions. For 90 years, we asked the wrong question: was this a battery? The right question was, what problem did this solve? That question led us to understanding. It led us to appreciation. It led us to recognition of ancient achievement on its own terms. As Turchen reflected in the team's final report, the Baghdad battery taught us that the most powerful tool in archaeology isn't ground-penetrating radar or carbon dating or DNA analysis. It's the ability to ask better questions. For 90 years, we asked the wrong question: was this a battery? The right question was, what problem did this solve? That question led us to understanding. It led us to appreciation. It led us to recognition of ancient achievement on its own terms. That's the real discovery, not what the artifact was, but how we learn to see it. This transformation in how we see the past has profound implications for how we approach the future. In an era of rapid technological change, environmental crisis, and global challenges, we often look to the future for solutions, new technologies, new theories, new approaches. The Baghdad battery reminds us that sometimes the most valuable solutions lay in the past, not as literal blueprints to copy, but as inspiration for how to approach problems with creativity, adaptability, and respect for context. Ancient peoples faced challenges similar to our own: resource constraints, environmental pressures, cultural conflicts, and developed sophisticated solutions within their constraints. Understanding those solutions doesn't mean rejecting modern technology. It means recognizing that human ingenuity has always found ways to solve problems, and that the diversity of those solutions can inspire new approaches to contemporary challenges. This perspective has already begun influencing sustainable technology development. Researchers studying ancient water management systems in Mesopotamia, Peru, and India have discovered techniques for conserving water in arid environments that modern engineering had overlooked. Architects studying traditional building techniques in hot climates have rediscovered passive cooling methods that reduce energy consumption without modern air conditioning. Agricultural scientists studying ancient crop rotation systems have identified practices that maintain soil fertility without chemical fertilizers. The Baghdad battery case has become a symbol of this broader recognition that ancient knowledge has value, that historical context matters, that the diversity of human technological achievement can inspire new solutions to contemporary challenges. As museums worldwide display the Baghdad battery with its new label Parthian electrochemical gilding cell, visitors encounter not a mysterious artifact, but a sophisticated tool that tells a richer story. The story isn't about alien intervention or lost super science. It's about human ingenuity, Parthian artisans observing material interactions, refining techniques through generations of experimentation, solving practical problems with elegant chemistry. It's about scientific collaboration, modern researchers from multiple disciplines and nations working together to solve a 90-year mystery through careful methodology and respect for evidence. It's about ethical partnership, Iraqi and Western scholars centering local expertise while enabling international collaboration. It's about educational transformation, students learning that genuine discovery requires patience, collaboration, willingness to be wrong, and commitment to evidence. It's about philosophical insight, recognizing that technological sophistication isn't about matching modern capabilities, but about solving problems effectively within historical constraints. This story doesn't diminish ancient achievement, it contextualizes it authentically. It recognizes that the Parthians developed electrochemical gilding because it served their religious and cultural needs. They didn't develop electrical lighting because they had no need for it. Understanding this difference is crucial for appreciating the diversity and sophistication of human technological achievement throughout history. The Baghdad battery's legacy will be measured not in volts or amperes, but in changed perspectives, in our ability to see ancient peoples not as primitive failures or recipients of alien technology, but as skilled problem solvers whose achievements deserve recognition on their own terms. The vessels and museum cases worldwide now tell this richer story, not of mystery or conspiracy, but of human achievement across millennia. They remind us that genuine understanding emerges not from sensationalism or speculation, but from careful science, historical context, and respect for evidence. They demonstrate that ancient peoples were neither primitive nor superhuman. They were practical problem solvers who developed sophisticated solutions using the materials and knowledge available to them. They show that technological sophistication isn't about matching modern capabilities, but about solving problems effectively within historical constraints. Most importantly, they reveal that the most powerful discoveries often come not from having all the answers, but from asking better questions. For 90 years, we asked the wrong question: was this a battery? The right question was, what problem did this solve? That question led us to understanding. It led us to appreciation. It led us to recognition of ancient achievement on its own terms. And in that recognition lays the Baghdad battery's true significance, not as a symbol of mystery, but as a testament to human ingenuity across all eras. The artifact discovered in Montourge's by Wilhelm Knig, studied for decades by scholars worldwide, and finally understood in March Malta by an international team of researchers, now belongs not to any single museum or nation, but to all of humanity, a reminder that our greatest achievements emerged not from isolation or competition, but from collaboration, curiosity, and respect for the wisdom of those who came before us. The Baghdad Battery is no longer a mystery waiting to be solved. It is a lesson waiting to be learned, a lesson about how to approach the past with humility, the present with curiosity, and the future with hope. And in that lesson lays its enduring legacy.